there's a reason for it going up. I don't remember if I have. Yes, here. What causes the pH to go up or down? Okay, so the pH will go down when organic acids are produced. Okay, that happens, for example, when you overfeed the substrate. It's going to start producing acetate. This is just an overflow system of the bacteria, and it's going to produce these organic acids. The pH will drop, and you want to maintain the external pH, so you have to add a base under those circumstances. Okay, if the bug runs out of food, if it runs out of glucose, okay, so this one here could happen from too much food. This is what happens with too little glucose food, carbohydrates. Bugs are into carbs. So if you don't give them enough carbs, they're going to take the protein, kind of like humans, except we humans kind of like protein. If you don't give it enough carbohydrates, it'll switch and start taking in protein for its sustenance. And as a result, it's going to produce ammonia and amines, which are nitrogenous, and then the pH will rise. So under those circumstances, what's the best thing to do? Any guess? Give it some food. That's right. It's just hungry. Feed it, and you'll be fine. All right. So I'll skip the next one because it's interesting, but it's not really. I mean, we are producing a protein, but we're really mostly producing cells, and our protein is inside the cells. So that's it. Okay. So in our process, I think I've already mentioned this, we are going to use ammonium hydroxide as a base to control the pH. Ammonium hydroxide is also a source of nitrogen, so that's a good thing for our bugs. And we don't really need any acid because we're not going to, if we get a pH spike, okay, this is what we wait for. During the beginning of the run, we wait for that pH to spike up, okay, that it's suddenly going to produce base. And if you remember what I just said, what kind of substrate is being consumed under those circumstances? Proteins. So if it's consuming proteins, we want to give it more glucose. So that's the point where it's eaten up all the glucose that we fed it initially, and it's time to turn on the food pump. All right. Okay, next is temperature control. Okay, this just shows, oops. Okay, this slide just shows that, you have in a very low density culture, this is a flask, and we're stirring it, okay. A low density culture, we have to add heat to get it to be the right temperature for the bugs to grow in, okay. As it starts to produce more bacteria, we need to control the heat, okay. We may need to add some, and we may need to remove some, but when we have a very dense culture, we need to remove the heat because the bugs are producing metabolic heat. Basically, they're combusting the glucose that you feed them. So they're taking glucose and oxygen, and they're converting that to CO2 and water, just like combustion. So they have their own little internal combustion engine to keep themselves working, and they give off heat as a result. So they're very efficient, but they do give off some heat. And so you got to take care of them, or they will cook themselves to death. So that's an important one for us to manage. So here's an equation that is basically based on yields. Okay, so this is the amount of heat given off, metabolic heat. Okay, and this is the volume of the culture, the growth rate, the concentration of bug in the culture, and this YH is related to the amount of heat that is given off depending on this particular substrate that they're eating. Okay, all right. So in a laboratory scale bioreactor, it's really very analogous to the large scale. There's just a different shape of the heat exchanger. Okay, we use a temperature probe inside the bioreactor, and we have a temperature controller, just the same. We use a heating jacket to heat up the outside of the bioreactor, and we also are going to use a little, pretty much just like this, a cute little heat exchanger inside of our bioreactor. It's a small bioreactor, so if we put cold water into that little heat exchanger, we flow water in and flow water out, and we're going to circulate it. And that will be between this cooling and the jacket heating, we will keep our bioreactor at the proper temperature. And we use an electrical heating jacket, not a steam jacket, but this is something like what you would use in a large-scale bioreactor. Okay. Okay, so here's some little bit of detail. 40 to 50% of the energy produced by the substrate catabolism is converted to ATP, and the rest is released as heat. So there is quite a bit of heat given off. And this is our respiration formula. Okay, can't forget about our nitrogen. If we produce cells, there's nitrogen in the cells, so we have to consume also ammonia. Okay, the heat of combustion of cells is 20 to 25 kilojoules per kilogram. So that is how much that it would take to combust the cells. So the reverse of that is going to be producing the cells. Okay, so